You know, we're swimming in electricity every single day, but have you ever stopped to think about the invisible forces behind it all? Forget the super complex physics for a sec. Today, we're going to break down the two amazing superpowers of electric current, the ones that literally run our world. So let's dive in. Okay, so let's say you want to show a friend how to build something cool, right? Like this classic steady hand game. You probably just grab a piece of paper and sketch it out. Here's the cell, here's the key, there's the wire loop. It kind of works, gets the idea across, but let's be honest, it's a bit of a mess, isn't it? And what happens if you need to share this with someone who doesn't speak your language? Or what if your drawing skills just aren't that great? There's got to be a better way, right? A universal language for this stuff so anyone, anywhere can look at it and know exactly what's going on. Well, guess what? There is. Before we can really get into electricity's awesome powers, we first have to learn how to speak its language. And that language is all about circuit diagrams. It's the super clean, super simple code that takes a messy sketch and turns it into a perfectly clear blueprint. Think of this as the alphabet for electricity. Every little part gets its own special symbol. Take the electric cell, for instance. See that long line? That's the positive terminal. And the short, chunky one? That's the negative. It's so simple, but so clever. And everyone in the world uses the same ones. And this is why it's so powerful. Look at the difference. On the left, you've got our scruffy little drawing. And on the right, the proper circuit diagram. It's the exact same circuit, but wow, so much cleaner, so much easier to understand. That's the beauty of having a common language in science. Now, you'll often see this symbol here for a battery. So what's the difference between a cell and a battery? Well, a battery is really just a bunch of cells holding hands. You line them up, connecting the positive end of one to the negative end of the next, and all that teamwork gives you a lot more juice for your gadgets. Okay, so we've got our language down, we can read the blueprints. Now it's time for the fun part. Let's flip the switch and check out the very first and probably the most common power of electric current, its amazing ability to generate heat. Just think about it for a second. When you switch on one of those old-fashioned light bulbs, there's a tiny wire inside, the filament, right, that glows super bright. That's the light part. That's what we want. But it's also kicking out a ton of something else as a side effect. Any idea what it is? Yeah, it gets hot, like really hot. And you know what? That's not a mistake or a flaw. It's a basic rule of the game. Whenever electric current flows through a wire, it creates heat. We call this the heating effect of electric current. And honestly, our entire modern world is pretty much built on this one simple idea. I mean, just look around your house. The heater that keeps you warm, the iron you use on your clothes, the toaster that makes your breakfast, your hairdryer, every single one of them works because of this. Inside, they've all got a special coil of wire, an element that's designed to do one thing really, really well: get crazy hot and radiate that heat when you run electricity through it. But, of course, all that heat isn't always what you want. Think back to that old light bulb. It was wasting a massive amount of energy just getting hot. That's a big reason we've all switched over to things like LEDs. They are incredibly efficient. Their whole job is to make a ton of light without making a ton of wasted heat. So this heating effect is useful for sure, but it can also be super dangerous. So how do we control it? How can one tiny little piece of wire be the thing that protects your entire home from a fire? Well, the big danger is when you get way too much current flowing where it shouldn't. This can happen if you overload a circuit, plugging way too many things into one outlet. Or it can happen with a short circuit, where the electricity finds a shortcut it's not supposed to take. Either way, the wires get dangerously hot fast, and that can easily start a fire. So what we needed was a hero, a guardian for our circuits. And that hero is the humble electric fuse. It's such a clever little safety device. It's basically designed to be the weakest link in the chain on purpose. Inside, there's this special wire that has a really low melting point. It's literally designed to fail. And here's the brilliant part. When a big, dangerous surge of electricity comes through, that special little wire inside the fuse gets hot instantly. And before the wires inside your walls have a chance to even think about catching fire, that fuse wire just melts. It breaks the circuit, the electricity stops flowing, and disaster is averted. It's so simple, it's genius. So that's superpower number one, heat. But electricity has another trick up its sleeve, a totally different secret power that was discovered almost by accident, and man, did it change everything. We're talking about the power of magnetism. This one goes back to a scientist named Hans Christian Ørsted. He was the guy who first figured out that electricity and magnetism weren't two separate things. Nope. He discovered that when you pass an electric current through a wire, the wire itself starts behaving just like a magnet. How cool is that?
And his big discovery came from a really simple observation. He just had a compass sitting on a table near a wire. And he noticed that every single time he turned the power on and current started flowing, the compass needle would suddenly jump and point right at the wire. The electricity was creating this invisible force field, a magnetic field.
And right there, that's our second superpower. It's called the magnetic effect of electric current. It's this core idea that a moving electric current always creates a magnetic field around it. And once scientists figured that out, it opened up a whole new world. Okay, so knowing that electricity makes magnetism is one thing. But the real game changer was figuring out how to control it. How do you actually use this to build a magnet that you can turn on and off whenever you want? Well, it's actually way easier than you might think. All you need is an iron nail, you wrap it up really tight with some insulated wire, and then you just hook up the ends of that wire to a cell. The second that current starts flowing, bam, the nail's a magnet. Got the power, and the magnetism disappears. You've just made an electromagnet. And these on-demand magnets, they are everywhere. I'm talking about the giant cranes in scrap yards that can lift entire cars. They're used to pull iron and steel out of junk. Doctors use incredibly precise little electromagnets to pull tiny bits of metal out of a person's eye. And yeah, they're also in something you probably use all the time, the electric doorbell. It's such a perfect little machine. It's just a rapid-fire cycle of magnetism turning on and off. You press the button, the electromagnet flicks on and pulls a little hammer to hit the gong. Ding. But hitting the gong also breaks the circuit, which turns the magnet off. The hammer springs back, which completes the circuit again. And the whole thing just keeps repeating super fast, giving you that brrring sound. So there you go, the two incredible superpowers of electric current. You've got the heating effect, which we've harnessed for everything from cooking our food to protecting our homes. And you've got the magnetic effect, which lets us build motors and lift massive objects with the flick of a switch. And that's just two of electricity's tricks. Really makes you wonder, doesn't it? What other invisible forces are quietly at work shaping our world every single second?